Good morning, students. Welcome back to our webinar session, physics, that we are discussing chapter 9, magnetic induction. And we are at Lenz's law. Okay. That the statement that already we discussed is very important. What the statement says: the polarity of the induced EMF is always such that it tends to produce a current which opposes the change in magnetic flux that produces it. See what we discussed in the last class, that whenever the magnet of North Pole is moving towards the coil with a certain velocity, then the EMF will be generated in the coil. Right? So due to this EMF, what happened? The magnetic flux magnetic field is generated in the coil. So that field, in which direction? North pole, means north polarity of this magnetic flux that opposes the magnet that we are approaching the coil. So what is the cause here? Keeping the magnet towards, moving the magnet towards the coil is the cause, is the reason. So what is here, what is happening here? Whatever the flux, whatever the magnetic field is generated due to the induced EMF, what it is doing, it is opposing the cause, opposing the reason. Okay, so with this, what we can conclude, that we can identify the direction of current and also it is opposing the cause, opposing the cause. So in this, we can identify the direction of induced EMF, direction of the induced EMF. Similarly, already we have seen this in the other day, that north pole is moving backward, means the magnet is moving backward, then the flux is inside, means magnetic field is inside this coil, then the current is a clockwise direction. Current is a clockwise direction. Okay? So this already we discussed, and this also we discussed with a more example. The induced current always flows in the direction such that it opposes the change which produced it. See, the point is, because of the change of magnetic flux, EMF is generated in the coil. So that is, what is the reason for producing EMF is changing the magnetic field. So due to the change in the magnetic field or flux, the EMF is generated. Then due to this EMF in coil, that produces magnetic field, and what is the directions of these magnetic fields are, left side is the north pole and right side is the south pole if the current or EMF is moving in anti-clockwise direction. Okay, if the flux is, EMF is moving in anti-clockwise direction, then left side will be north and right side will be the south, will be generated in the coil. So once this north pole is generated at this side, then the magnet is also north pole is then both the north poles will be repel each other. Both the north poles will be repel. Okay, so here the coil repels the magnet. See, when N pole, that is north pole of the magnet, is moved towards the coil, end of the coil becomes north pole. End of the coil becomes north pole. And if you see right side, if the magnet is moving away, when the magnet is moving away, then the EMF moving away means what? Change in magnetic field. So then EMF will be generated in the coil. This is observed, this arrow marks is it. Project clockwise direction. The current is moving in a clockwise direction. So once in the coil, the EMF is moving in the clockwise direction, then the current is moving in the clockwise direction, then left side will be south pole and right side will be north pole will be generated. So look at this diagram now. The north pole of the magnet is moving towards, sorry, actually it's moving away, and due to this south pole, means the coil of this part is becomes south. Then what is happening here? South and the north will try to attract. See, in this diagram, if magnet is moving towards, then repels each other, and if the magnet is moving away, then attracts each other. Okay, so always what is doing here, this EMF, what EMF is doing here is, it is opposing the cause. It is opposing the cause. Here the magnet is approaching, but it is not allowing. The coil is not allowing. If the magnet is moving away, here also the induced EMF is not allowing. Okay, it's not allowing to move away because it's attraction happening here. Okay, so this is already discussed in the last class. And finally, okay, so final conclusion of this concept is see, when the magnet approaches the coil, when the magnet approaches the coil with the north pole, the coil approaches the coil with the north pole, then the direction of induced current is anti-clockwise. So what Lenzler says, it says about the direction of induced current. Okay, direction of induced current, and also it always opposes the cause. Opposes the cause. Okay, so here when the magnet then the direction of induced current is anti-clockwise, such that phase of the coil is towards the magnet behaves as a north pole. This point you should understand. Yeah, look at this diagram. Look at this diagram. Here, magnet north pole is facing the coil here. This is the coil. This is the magnet moving with a certain velocity. North pole is moving towards the coil. Look at this. If north pole is moving towards the coil, see the direction of current here. See the direction of current. So direction of current is anti-clockwise. Direction of current is anti-clockwise. Then see, use this diagram, right hand thumb rule. So if the current is moving in this direction, thumb direction, see, observe this curved finger direction is the magnetic field. Okay? Yes, sir. Right. Okay, so the same thing. The current is moving in this direction, then magnetic field. Look at this magnetic field. Okay, magnetic field. Right? This is external magnetic field, and this is induced magnetic field. So if this is anti-clockwise, then upper part of this magnetic flux means this magnetic field is due to the induced current. The magnetic field is due to induced current. So due to the induced current, the magnetic field is generated. So upper part of this coil becomes north polarity. Upper part of the coil becomes north polarity. So north and magnetic north. So this magnetic north and this induced magnetic field north, both will repel. Actually, this is moving towards the coil, but what the coil is doing, it is repel. Okay, it repels the magnet. Now look at this. Now same magnet is moving away. Then what happens? The flux will be changed. So due to change in flux, what happens? The current will be generated. That is, induced current will be generated. So that induced current now it is in a clockwise direction. Now it is in a clockwise direction. Then once it is clockwise direction, see, observe then the magnetic field due to the induced current is become south polarity. Then this is south polarity and this is north pole of the magnet, both will attract. Means this induced EMF is not allowing the magnet to move away. Not allowing to this magnet to move away. So here what is going here? EMF is opposing this cause. Similarly here, now the polarity of this magnet opposes the cause, means it is moving forward, moving coming to the coil, but it is repels. Here moving away from the coil, it attracts. So this is what is indicates the direction of current which is flowing. Here, if you observe the symbol is given N here, this is S here, that you can see here very clearly. Observe this. Right? So when magnet, north pole of the magnet is approaching the coil, then it is anti-clockwise direction. The current is, induced current is anti-clockwise direction. See, the induced current when the magnet enters the coil of wire, then it is in anti-clockwise direction. Yeah, look at this. How to identify the poles of the electromagnet. See, if the current is in anti-clockwise, the red one, okay, if the current is in anti-clockwise, then that side will be magnetic field polarity will be north. It looks like north, right? And if the current is flowing in clockwise direction, then that side polarity will be, means coil, that side polarity will be south. So identify these things whenever the situation comes, then use this phenomenon. Okay, so especially actually the solenoid concept is not there in the syllabus right now. If the solenoid is there, then this picture means this phenomena is lots that we can use out there. It's compulsory that we should understand in which direction the current is flowing, so that that polarity, that side of the polarity of the magnetism, that we should understand. Okay, so this is about, I'm repeating this, if the current is flowing in anti-clockwise, then that side of the coil will become north polarity, and if the current is moving in a clockwise direction, so that side polarity will be, polarity of magnetism will be south. Okay, so that is explained with this rule. See here, the magnet is moving forward with velocity v. Then what happens? The flux is changing continuously. Then in this coil, the current is moving. The current is moving in anti-clockwise direction. The current is moving in anti-clockwise direction because the north is moving towards the coil, anti-clockwise direction. Then the magnetic field, observe this, magnetic field will be what? In which direction? See, this is anti-clockwise, then this will be north. See, this is anti-clockwise, then it will be north. Right? So this north will be repelled. So this will push back this magnet. Okay, we'll move on to next now. So similarly, if the magnet is taken away from the coil, then face of the coil towards the magnet, the induced current flows in clockwise direction. I'm repeating, if the magnet is taken away from the coil, okay, then in the face of coil towards the magnet, the induced current flows in anti-clockwise direction. That's what we discussed. Hence, that face of the coil behaves like a south pole. Yeah, look at this. Okay, so and the previous examples we discussed with the north pole is moving and away from the coil. Now south pole, how south pole will become? See, south pole is approaching the coil. South pole is approaching the coil. Then this will be clockwise direction. This will be clockwise direction. Then this will become, means the polarity of this magnetic field will become south, and both will repel each other. Similarly, if the south is moving away, then this will become north. Means the current flow is in anti-clockwise direction. Then what happens? Both will attract. So here observe this galvanic deflections. So it is moving forward. The magnet is moving forward. It shows in one direction. If it is moving another direction, in the opposite direction, then the deflection shows in exactly opposite direction. Okay. So what is this deflection which says that? Direction of current, direction of induced current. Okay. So here it is in a clockwise direction. Here is in an anti-clockwise direction. Okay. Right. So with this, what we understood that whenever there is a change in magnetic field, change in magnetic flux, then induced current will be generated, and Lenz's law expands about the direction of current, means in which direction, whether it is clockwise or anti-clockwise, which direction the induced EMF or current is flowing in the closed circuit. Okay, so the terms that you should understand here. Induced EMF can exist whether the circuit is open or closed, but induced current can exist only in the closed circuit. Okay, so we should understand what is EMF and what is current. So induced EMF means when the magnetic field is changing, then inside the coil, EMF only EMF will be generated. Okay, only EMF will be generated. I am repeating, when the magnetic field is changing, okay, magnetic field is changing, in the coil, only EMF, first EMF will be generated. Then if that EMF means the two ends of the coil which are connected to any external circuit, any load or any other device, then only if it's closed from one end of the coil to the another end of the coil, it's connected with another conductor or another load or any other device, then if it is closed, then only the current will flow. That would be induced current will flow. Okay, so induced EMF is different, induced current is different. But current may not exist, but EMF definitely exists whether the circuit is closed or open. Circuit is closed or open. Open means what? The two ends of the coil may be connected or may not be connected, but at the two ends of the coil, definitely EMF will be generated. Okay, that's what is the note. Induced EMF can exist whether the circuit is open or closed, but induced current can exist only where it is a closed circuit. Okay, so this is the point. And yeah, so here is one of our applications in the electromagnetic induction. So here, see, this is a title motional electromotive force. Motional electromotive force. This is a small experiment and a small application. Right? How we are using Lenz's law. It is the experiment to support that the induced EMF. It is the experiment to support that the induced EMF developed when the moving conductor cuts the magnetic fields. I'm repeating, it is experiment that supports that induced EMF develops. Induced EMF is developed when the moving conductor cuts the magnetic field. Just look at this experimental setup, then we will see this. Okay, here in this experiment, what we are going to do is by moving directly. What is the Faraday's laws and all, that whenever there is a change in magnetic field, there will be current will be induced with the coil. Okay, so this is the point. Now here, without changing the magnetic field, so here we are creating an induced current. This is one of the applications. Okay, see here, Mn are the two metallic rods. Okay, and SR is also a rod connected. Totally the setup is in a U-shaped setup. Okay, MSRN is a U-shaped rod, okay, frame, metallic frame. On that PQ is the rod. Okay, it's a conductor, is kept on the frame, Okay, now this PQ is the rod is movable. Okay, it's a frictionless area. That is, it's a movable. It can move easily. And see, look at this. When this PQ rod is kept here, okay, and it is movable on the either sides. Now, from this PQ rod, this whole frame looks like a rectangle shape. Have you observed? So this rectangle will become what? PSRQ. This rectangle will become PSRQ. So this is the rectangle. Now the whole setup is kept in a uniform magnetic field. So you can see all the cross here. Okay, all the cross means what? The magnetic field is moving inside the paper or inside the board. Okay, magnetic field, capital B, uniform magnetic field. So the whole setup is kept in the uniform magnetic field. Now observe these lengths ones. SR is the width of the frame, that is X is fixed one. Okay, and this QR is the displacement, means length. Okay, for example, SR is the width and RQ is the length. Okay, so this length can be changed by moving this rod. Okay, by moving this rod either inside or outside this U-shaped frame. For example, if it is moving inside like this, okay, then the size of this rectangle is decreasing. So this value is changing. See, let me explain. Let me explain the concept and try to understand. Here, it is a magnetic flux. What is magnetic flux? We have a formula. Okay, pi is equal to integral B dot dA. B is the magnetic field, dA is the surface area. Okay, so magnetic flux means what? Number of lines of force present or passing through a closed surface area. Okay, so here the number of lines fixed in this rectangle, okay, is changing if this rod is moved. If the rod is moved either sides, then the number of lines of force which are present in this closed rectangle shape is changing, right? So if this is fixed, PQ is fixed over there, then the number of lines of force which are entering per surface area will be fixed. If PQ rod is moved, if the rod is moved on either side, then definitely the size of this rectangle area is changing, then the magnetic flux which is entering into this also changes. Okay, now what is Faraday's laws and Lenz's law saying that whenever there is a change in magnetic field or change in magnetic flux, okay, there will be induced current be generated. So here we are not changing the magnetic field, but we are changing the surface area. We are changing the surface area. We are not changing the applied magnetic field. Applied magnetic field is a uniform magnetic field, is a fixed. But if you change this rod, then the area of cross section is changing. Then the number of lines of force which are present in this coil is also changing. Then what happens? In this metallic frame, in this conductors, the EMF will be generated. EMF will be generated. So this is what is our application of physics. Yeah, look at this now. The induced EMF developed when the moving conductor cuts the magnetic field lines. Means cuts the magnetic field line means it's approaching across the magnetic field lines. Understood? So the magnetic field is perpendicular to the paper and okay, perpendicular to the paper means inside the paper. Then rod is moving across the magnetic field. Okay, so it is at a level. Then the size of this rectangle is changing. Then automatically the number of lines of force which are entering into this surface area also changing. So the PQ is the straight conductor moving with the speed v with no friction. Okay, in a uniform magnetic field B on a U-shaped conductor as shown in the figure. Now this setup forms a rectangular closed loop because altogether it is a metal, so conductors, then it is a closed loop. Okay, now look at this. So let the QR, observe the diagram, let the QR, where is that QR? Yes, it's a horizontal one. QR is, let us take X here and RS. Let us take L here. Okay, now, so product of these two will gives the surface of this rectangle. When the rod is moved, towards the left with a constant velocity v, then the area of the rectangular loop changes with time. Okay, slowly you are moving, we are making this PQ rod move towards the means inward towards the left side of the diagram. Okay, then area of this loop also changes with time. Then, as we know, the magnetic flux linked with the closed surface is changing. Then EMF will be induced in the circuit. Yes, as we know. Okay, as per the Faraday's laws, as the magnetic flux is linked with the closed surface, magnetic flux is linked with the closed surface, then which is changing with the time, magnetic flux is changing with respect to time, then EMF will be induced in the circuit. EMF will be induced in the circuit. This point already know. So that's what is happening here. Okay, that's what is exactly happening here, the change of magnetic. Here we are not changing the field, but we are changing the surface so that number of lines of force which are entering into the circuit, entering into the loop will be changed. Okay, so we know this formula pi is equal to B dot ds. Okay, B is the uniform magnetic field and ds is the change in surface. So that you can rewrite like this: B ds. Ds means what? Ds is the area of the cross section. So area from this diagram, what is the area here? L into x. Okay, L into x is the area. So we can write E as a Lx. So simply, what is this? Blx is the pi. Okay, Blx is the amount of flux which is passing through the closed loop, that is rectangular. Now, since the rod is moving, observe this. Since the rod is moving, then the value of x changes with time. The value of x changes with time. See, this is moving like this, then x also changes. X is initially, for example, 10 centimeters. Then as this is decreasing, then it will become 9, 8, 7, like this. So area means x is changing with respect to time. So the flux also changes with time, and EMF is induced in the moving rod. Okay, so then what happens? Then due to this change in magnetic flux, EMF will be induced. EMF will be induced in this rod. Okay, in this rod. Now, this reminding these wires are closed circuit now. This is wire, this wire is a closed. Initially at this rod, in this rod, what happens? EMF will be generated because EMF is only this rod only moving. This rod only moving forward. Then EMF will be generated inside this rod. And the remaining this pink color thick line is nothing but what is a closed circuit, means another metallic frame, that is conductors are connected like this. Then this is closed loop now. Okay, so then what happens? The current will be flowing through. That's what I told you, the difference between induced EMF and induced current. So here inside the rod only induced EMF will be generated, and this wire is connected on the either sides of this. Then the current flows through this. Then the current flows through this. See, this is induced current and this is induced EMF. So the expression for the induced EMF is, see, already you learned this in Faraday's second law. Okay, Faraday's second law, EMF is equal to minus d pi by dt. I told you minus is what? It is indication. What it indicates that it is always opposes the cause. Okay, so EMF is always opposed to the cause producing it. So that's why here it's negative sign indicates only the direction. Okay, so expression for the induced EMF is d pi by dt. Okay, so just now we obtained the pi value, that is Blx. So substitute this Blx here. So in the place of pi, substitute Blx. Then magnetic field, uniform magnetic field is constant, and the length of width of that frame, okay, coil is also fixed. But who is changing? X is changing with respect to time. Only x is changing with respect to time. So constants are taken out. Then only the variable dx by dt. Okay, only x is varying with respect to time. So since x is changing, then so finally after deriving this, okay, dx by dt means what? Rate of change of position. Okay, rate of change of position. X is position. So for every time position is changing. Okay, the rod position is changing. So this is rate of change of position is nothing but velocity. Okay, so finally E is equal to minus BLD minus BLE. So since E is a dx by dt. So what is this? EMF is equal to minus BLE. This is what? Motional EMF. Motional electromotive force. Motional electromotive force. So this is EMF expression in a metallic frame. Okay. So this is this much EMF is generated. So in this minus is what? Is always opposes to the cause producing it. B is the uniform magnetic field. L is the width of the metallic frame, and V is the velocity of the rod which is moving on. Right? So this induced EMF, the value is minus BL. This is quantity. Okay? So minus indicates what is only the direction. Okay, so the induced EMF BLV is called motional EMF. Motional EMF. So if you observe the diagram, the rod is moving. The rod is moving. PQ is moving. So while it is moving, the induced EMF is generated. So this is why it's a motional EMF. So thus EMF is induced by moving a conductor instead of varying the magnetic field. So initially I told you that instead of changing the magnetic field, what we have done, we have changed the surface area just by displacing the rod. By displacing the rod, we have changed the magnetic flux present in the coil so that induced EMF is generated. So this is what is a motional EMF. Motional EMF. Okay, so this is this can be written in a vector form, that is E is equal to L dot V cross B. Okay, right. So this is what induced motional EMF. Okay, next is eddy currents. It's very important eddy current concept. Right, we see this eddy current. When a bulk piece of conductor is subjected to a change in magnetic flux, then induced current produced. So the point is, up to now we discussed only with the help of a coil. Only with the help of a coil. I'm repeating, up to now we created induced current or induced EMF by taking coil as an example. Okay, only coil, and we identify the direction of current. Okay, so we also identified the magnetic field, direction of magnetic field. Okay, if the magnet is moving towards the coil, then current will be in anti-clockwise. The upper side of the coil will become north polarity. These things we discussed in the title of Faraday's laws and Lenz's law. Now the same thing we are applying this in another manner, that instead of a coil, if we consider a metallic block, okay, metallic plate, means metallic plate is simply there is no direction. Simply say just like a block, just like a block. So in such materials, how we can say that in which direction the current is flowing? Just square shaped, for example, square shaped. Okay, a metallic block is there. If it is kept near the changing magnetic flux, okay, changing magnetic flux. So magnetic flux is changing. In that place, if you are keeping a metallic block, will it produce the current? Will it induce the current? That's what is an eddy current concept. Yes, that metallic block also produces current. Okay, so those currents are called eddy currents. So that will see. So when bulk piece of conductor is subjected to a change in magnetic field. Remember, we are not using coil here. We are using only pieces. Okay, bulk pieces of any conductors, metals. Okay, when they are subjected to external change in magnetic flux. So we know what happens when the magnetic flux is changed. Then inside the coil, if you consider the coil, then it was a current will be generated. But here we are not taking coils, we are taking conductor pieces, bulk pieces of conductors. Okay, there are no shapes, means particular different shapes. Now, yeah, the flow pattern of the induced current. See, the question is, in the coil, we can identify the direction of current. But in a blocks or metallic plates, how we can say that in which direction the current is flowing? That's what. The flow pattern of the induced current in the metal block is similar to, this point is very important, is similar to wells. Okay, wells in the water. I've seen the wells in the water, right? Similarly, it is spiral pattern. Okay, spiral pattern. Okay, so the flow pattern of the induced current. Remember, I'll tell you see, in a conductor or in a metal block, all the electrons are free. Okay, mostly in the conductors, there will be lots of free electrons present. Now these free electrons, at no external field, they will move in a random direction. Whereas when the block or conductor is placed in the external field, then what happens? They are aligned, the electrons are aligned to move in a particular direction. Okay, aligned to move in a particular direction. So that alignment in this case will be in a spiral form. Okay, where? Okay, so I'm repeating the flow pattern of this induced current. I told you the current is because of the flow of charge. Okay, so charge is nothing but electron. So all these electrons are aligned to move in a particular direction. So, okay, so this direction will be means the shape of this motion will be what? Well in the water are simply say spiral pattern. Now, see, these currents are called eddy currents. These currents are eddy currents. What is eddy current means what? This induced current is generated in the metal blocks due to the change in magnetic field. Those currents are called eddy currents. Okay, so this was discovered by the scientist Foucault, and this current can also be called as the Foucault currents. Don't confuse it. Sometimes in the examinations, instead of asking eddy currents, you may ask write a short note on Foucault currents. So don't confuse. Okay, so instead of asking eddy currents, they may ask to write a short note on Foucault currents. So that's why it's don't confuse here. So it was discovered by the scientist Foucault. So that's why the name is a Foucault currents. Okay, so we'll move on to the next here. Look at this. So here is an experiment for more understanding. Look at this. A copper plate is allowed to swing like a simple pendulum between poles of a strong magnetic field. See, we are practically doing that. Yes, now I explain the concept that taking a metal block and keeping it in a changing magnetic field, then what happens? The induced EMF will be generated. Yes, so this induced EMF produces the current. Already we have seen that in coils, but now we are applying that into the same concept to the metal blocks. So how it will be? Okay, see, it is an experiment, it is an example here. Look at this. The south pole is a magnet and here is the north pole. Okay, so in between we suspended a metallic plate. With a pivot. Okay, right. Then what happens that it is allowed to oscillate between the two poles of the magnet. Allowed to oscillate between the two poles of this strong magnetic field. Then usually, look at this, usually when it is a simple harmonic motion, simple pendulum arrangement, then it is continuous to oscillate. Continues to oscillate. Means, for example, for example, this simple pendulum allowed to move for 10 oscillations per second. Okay, if the simple pendulum is making 10 oscillations per minute, and when the external magnetic field is kept like this, okay, external magnetic field is kept like this, then per minute it may do only 4 oscillations. 4 oscillations. Observe, when the no external magnetic field is present, this metallic block or metallic plate can oscillate 10 oscillations per minute. But when the south pole, means magnetic poles are kept near that, then it can oscillate only 4 oscillations. Then what we understood? Then this external magnetic field opposes the motion of this metallic plate. Okay, so what is happening, we'll see now. Right, so arrangement is what? Allowed to swing like a simple pendulum between the two poles of a strong magnetic field. Okay, look at this now. See, we are applying this Faraday's and Lenz's law concept. Yeah, this is a metal plate, not a coil. Right, so this is the metal plate. See, observe from this part. Observe this. It is away from the magnetic field, means far from the magnetic field. Far from the magnetic field and is moving towards the magnetic field. Moving towards the magnetic field. Magnetic field means what? Between the north pole and south pole, lines of force are passing through. So this metallic block is entering into the lines of force. Into the lines of force means what? Change in magnetic flux. Into the lines of force means what? Into the magnetic field means what? Magnetic flux is changing. Magnetic flux is changing. What happens? What happens? It includes current. So due to includes current, what happens? Magnetic field will be generated. What that magnetic field will do? Opposes this cause. What is the cause? This metallic plate is entering into the field is the cause. Okay, this metallic plate is entering into the field is the cause. So this cause is opposes Lenz's law. This cause is opposed by this magnetic field is generated inside the coil due to the inducement. Okay, I am repeating, the metallic plate is very far from the magnetic field. Now it is thrown into the magnetic field, then lines of force which are entering into this metallic plate changes, then is nothing but change in flux. So whenever there is a change in flux, what happens? The current will be induced. So inside the metallic plate, there will be more number of free electrons, I told you. So all these free electrons are aligned to move in a particular direction. Then once they are in motion, then what happens? The current will be generated, and due to that induced current, what happens? The magnetic field will be generated, and this magnetic field opposes to move into the magnetic field, into between the two poles. But anyway, due to the gravitation, this metallic plate will enter into the field. So reaches the center and comes out with the same gravitational force. It will move out of this field also. See, while it is moving out of the field, then the direction of current is changed. Out of the field, direction of the current is changed. See, observe, while entering into the field, between the two poles, it is in the anti-clockwise direction. While it is leaving from the poles, then the direction of current is clockwise direction. So that's why in the Lenz's law we discussed, means we use those many examples because to know the direction of current, so that the direction of magnetic field. Okay, so the current direction in this will be anti-clockwise, then this will become, so you know the polarity, that is anti-clockwise and north pole, and so it is in the clockwise direction, it will become south pole, right? So then what happens, while it is leaving, it is anti-clockwise, then the polarity of the magnetic will change, and what is the cause of producing this magnetic field is leaving. But this change in magnetic flux means this magnetic flux, magnetic field is generated inside, that won't allow. What is the length law? It is opposite the cause produced it. See, in this, it is moving, entering into this, it is not allowed, and here it is leaving the magnetic field, also not allowed. Also not allowed. Understood? So in both the cases, while it is entering in between the two poles is not allowing, while it is leaving this metal plate is also not allowing, because what's that, magnetic field directions are changing. So with a more elaboratively, you can see these three examples here. See, it is entering here and strictly it is not allowed. So that much freely it is not entering into the between the two poles. And anyway, it is left, this one is also, it's not allowed. Okay, so the velocity is changing at every time. Okay, then without a field, it may make 10 oscillations per minute, but now the field is present, then it will take only almost 4 to 5 oscillations. Then with this, what we observe that it is not making a free oscillations. It's not making, it's unable to do the free oscillations. Okay, so these oscillations are called damped oscillations. Oscillations are damped, means slowly with respect to time, number of oscillations decreases and comes to zero. Okay, so here it is found that the motion of the plate becomes damped and comes to rest in the field due to electromagnetic induction. What is electromagnetic induction? Due to the change in magnetic flux, induced current is generated. That's what.
Into the session, sir. Time.
So it is found that the motion of the plate becomes damped and comes to rest in the field due to electromagnetic induction. Okay, so we will stop with this and we will continue the next class. Okay, so thank you all.
Thank you, sir.